So let us talk about edge detection. So finding or detecting the edge in an image is edge detection. What exactly edges are? These are the places in the image where intensities are changing rapidly. This may be from the high intensity to low intensity and vice versa, from low intensity to high intensity. So exactly what constitute an edge can really be a domain dependent. And this in this particular figure, this is a model of an ideal digital image, and this is a model of a ramp image. See that the intensities are rapidly changing, and here intensity are gradually changing. Therefore, we have a ramp edge here, and here we have a very sharp transition of the edge. So there are edge operators, a special filter which enhances these discontinuities or the shift of the intensity. These are the edge operators. For example, first derivative, that is del fxy by del x. This is equivalent to fx plus 1y minus fxy, that is minus 1 and plus 1 in the form of the filter. And this edge operators enhances high spatial frequencies. This edge operator, actually they are employed to enhance the high spatial frequencies. We may recall the equivalent filter in the frequency domain. What it does, Tn to the power fx dxn, that is 2 pi ju to the power n of fu. So for first derivative, that is n equal to 1, this acts like a high pass filter attenuating frequencies which is near 0. So this is the form of the edge operation. This edge operator also enhances noise. This is the main problem. Edge operators enhances the edges. It's very fine, but they enhance the noise also. For example, first and second derivative of a noisy ramp edge. This is the original image, and this is a cross-sectional profile. This is our edge, and this is the cross-sectional profile. This is the first derivative. See, there is a sharp change, this is a sharp change, so we'll have a sharp change and sharp change. And the derivative of the first derivative will get only one point line here, one line here. And in this, we are increasing some noises. Let us increase the noise in this way. So we have just added some noise here. If you can see, more noise here, and you know, a lot amount of noise we have added here. Now small amount of noise, the first derivative, okay, we have certain noise here, but this second derivative is far beyond our comprehensions, because it actually enhances the noise to a level which is not usable. In this particular case, again we have added the noise, and the first derivative itself is unusable. We cannot use it. And the second derivative, there is no question about it. So first and second derivative of a noisy ramp edge we have seen, even with the very low noise, first derivative is useless at this noise level, as we have just seen, and the second derivative is useless for even lesser noise. Even for a less noise, first level noise, it is unusable. So these are the problems. Then we have this edge detection. Practical edge detectors first do image smoothing for noise reduction. Maximum edge detectors, before they can actually detect the edge, they do image smoothing for noise reduction. For example, this Sobel filter, if this is gx direction, and this is -1, -2, -1, this is gx, and this effectively does something followed by differencing. So 1 to 1, this is smoothing, and then this area. So what will be the gy? This is -1 for -2 and 1, and this is 1, 2 and 1. This is y direction plus. So what we do, gx plus gy square and under root. This is how we find the Sobel edge detection. So all edge detectors do smoothing for noise reduction and detection of candidate edge points, followed after smoothing. This is followed, and then edge localization, that is keeping only the points that are closest to the true edge. This is done by most of the edge detection. This is the Sobel. I just told you how it is performed. The Sobel edge detector example is there. Example image, original image is this. What we do, we find the gx or fx in this case. This is a MATLAB expression or a code. So fx square plus fy square and under root means cap by 0.5. So it does the same thing, and we get the image like this. This is del f by del x whole square plus del f by del y square. This is gx, this is gy under root. So this is how we get the gradient magnitude using Sobel mask. This is not very much appreciable, but still, even if it is not appreciable, we are getting the edges. The edge detection is going on. This is what we wanted. Now, threshold edge operator results. We can threshold edge magnitudes to produce the binary image. This is low thresholding, this is high thresholding, and this is non-maxima suppression. So we get a single line here. So problem is that we only want one response to one edge. We don't want just for one edge various responses. So the solution is to take the point that is the local maxima of the gradient magnitude. This is very important. So in the direction of the gradient, we take the local maxima of the gradient magnitude. This is edge thinning. So we take only the local maxima in the direction of the gradient. How it is done? This MATLAB edge function does this. If this is the direction, let me draw it for you. If this is the direction, this is the direction of the gradient. So these points are local maxima in the direction of the gradient. So this image is a good example. This circles bright dash.png. So we just take the inverse of fx, fi by fx. This is a gradient, and we just find the floor of this. So that we can just get the local maxima, and others we just ignore or get rid of. So this is finding the theta, that is the gradient, del f by del y, del f by del x, and this is how edge thinning can be done, because we don't want these to be very these edges to have a good width. We just want one line, and that is enough for us to find a edge or see as a image as an edge. So scale space edge operators are also there, and we really require these scale space edge operators. This intensity changes occurs at different scales in an image, so we need operators at different size or to detect them. Somebody may be interested in this point only, somebody may be interested in this point only. So there has to be scale space edge operators. So scale space means the space of the images created by applying a series of operations or operator of different scales, and these Gaussians of different sizes can be used to defilter the image at different scales. This is Gaussian is very important. See if this sigma is increasing, and convolving with Gaussian blurs the image, wiping out all structure much smaller this sigma. If you apply this sigma to this, you will get, I'll show you. This is first sigma, this is second, one more sigma, this is again sigma values are increasing. So finally, convolving with this Gaussian blurs the image, wiping out all the structures much smaller than this sigma. So you can apply this G sigma xy, which is the Gaussian. So these are the Gaussian operators. Why we are interested in Gaussian operators? Because Gaussian is the only operator that is localized in both the spatial and frequency domain. Let me read it for you again. This is very important line. The Gaussian is the only operator that is localized in both the spatial and frequency domain. This is the spatial domain, this is the frequency domain. See, this is localized in both the domains, right? Even this 1 by 2 pi sigma square e to the power minus x square plus y square by 2 sigma square. Again, you have e to the power minus 2 pi square sigma square u square v square. So this is being localized. It becomes 0 somewhere, but the shape remains almost the same. So now we can apply this Laplacian of a Gaussian because of this property of Gaussian. This is also called as Mcgraw-Hill. This Laplacian of Gaussian is also called as Mcgraw-Hill. Please remember this. So this is the Laplacian, and this is the Gaussian. So we apply Laplacian of Gaussian. So we convolve with the Gaussian, we convolve this with the Gaussian and take the Laplacian, or do the equivalent operation, right? Maybe in this way or this way. We can apply this convolution and then apply the Laplacian, or rather you can apply directly Laplacian to G and then convolve with the image. So this Laplacian of Gaussian, the operator scale is determined by this sigma. So when you change this sigma, the scale will change. As we suggested that we need some really important edge operator to be working on different scales. This R is nothing but R. This R square is x square plus y square. So this negative inside this circle and positive outside circle is going to 0 at infinity. And this 0 is at radius r equal to under root 2 sigma. And this R actually varies the scale. Right? Now coming down to this figure. This particular figure, I'm trying to depict you the Laplacian of Gaussian. This is a 3D plot. This is the image. Black is negative, gray is the zero plane, and white is the positive. And this C is the cross section showing zero crossing. These are the zero crossing, and this is the 5 by 5 mask approximation to the shape of A. This shape. This is the 5 by 5 approximation. Now coming to zero crossing. The zero crossing in the convolved result indicate presence of an edge, right? If it is zero crossing, then we say that there is an edge. So this is an example function of smooth step edge. Peak is the first. If you take the first derivative, this peak is the first derivative. These are equivalent to the zeros in the second derivative, as like this. The magnitude of the edge is proportional to the slope at the zero crossing. So first derivative is this, and this particular portion will correspond to this portion in second derivative, and this will be zero. This zero crossing, and again this is for the second portion of the graph. So this is showing that there is a zero crossing. Now here we have this A as the original image. This is the Sobel gradient, which is just shown just for the comparison how Sobel will look like. And this is the special Gaussian smoothing function. This is the Laplacian mask. This is LOG, that is Laplacian of Gaussian. This is the thresholded LOG, and these are the zero crossings. So there are problems with LOG, that is Laplacian of Gaussian. The location of the edge is affected by nearby corners. So example is zero crossing locations near a corner. If you apply it near the corners, so there will be a bulging. You will find the result like this. So this is a problem with the LOG. Now we turn to the Canny Edge Operator. So we can derive the optimal edge operator to find step edges in the presence of white noise, where optimal means what does Canny Edge Operator optimal means? Good detection, that is minimizing the probability of detecting false edges and missing real edges. Also good localization. What does this good localization means? It is detecting edges that must be close to the true edges. And then single response. What does it mean? Return only 1 point for each true edge point. So good detection, good localization, and single response. This is what Canny Edge Operator suggests. So what is the Canny's analysis? This Canny was, this presented in 1986, so it's still young. So Canny's analysis is that he simulated step edges with additive white Gaussian noise. Once again, he simulated step edges with additive Gaussian noise and did numerical optimization to find the optimal edge operator. He found that a good approximation to the optimal operator is the first derivative of the Gaussian in the direction of the gradient. This is similar to LOG but doesn't use Laplacian. So this is the derivative of Gaussian. The gradient of the smooth image is given like this. So the gradient operator is like this, and the graph is seen here. So an edge point is a peak in the magnitude of the gradient of the smooth image in the direction of the gradient. So we then suppress non-maxima along this direction that we have already done. So this Canny Edge Operator convolve image with derivative of Gaussian operator. So ultimately it is essentially using this Sobel version only. So finding the gradient direction at each pixel, then quantizing into one of the four directions: north, south, east, west, northeast, southwest, and northwest, southeast. Right? All the four directions. And if magnitude of the gradient is larger than the two neighbors along this direction, it is a candidate edge point. This is what Canny Edge Operator shows. So these points are, this is two possible orientations of a horizontal edge in a 3 by 3 neighborhood, right? This can be edge, this can be edge, and this is the range of values of alpha, the direction angle of the edge normal for horizontal edge, right? For horizontal edge. And this is the angle range of the edge normal for the four types of edges directions in a 3 by 3 neighborhood. Each edge direction has two ranges shown in this corresponding, this or this, this or this, this or this, this or this, showing the corresponding shades of gray. Then comes the Edge linking. This is the second part. We want to join edge points into connected curves or lines. So this facilitates object recognition. So the problem is some edge point along the curve may be weak, causing us to miss them. This actually happens in Sobel. So this would result in a broken curve. So the solution, what Canny has given, we use a high threshold to make sure we capture true edge point and give this detected point like additional edge points into contours using a lower threshold. This process is called as hysteresis. So algorithm will be like this: find all edge points greater than t high. For each strong edge point, follow the chain of connected edge point in both directions perpendicular to the edge normal, and mark all points greater than this t low. This is the example where we can compare this LOG to Canny, and we try synthetic image of a white square on a black background. So this is how MATLAB treats the LOG, and this is how the Canny works. These are the simple example. This LOG for sigma equal to 15. This is for 15. See, this is the bulging out of. These are the problems in LOG. But still, we cannot get rid of this. But Canny is giving a good solution. In one more image, we can try this, and let me just show you the results. This is, various things are there so that we can find out the edges. This is LOG for 1, Canny for 1. You can see the difference. This is LOG for this sigma 2, and this is 2. You can see the difference. So always Canny gives the better result. So the summary is that edge points are location in the image where the intensity changes rapidly. And edge operators they use special derivatives to detect these locations, and it is useful to be able to detect edges at different scales depending on the features of the interest. So we can adjust the sigma of a Gaussian low pass filter in a convenient way to select the scale. So this was idea about your edge detection. Thank you so much. Take care.